Welcome to the I Can't Sleep podcast, where I help you drift off one fact at a time. I'm your host, Benjamin Boster, and today's episode is about welding. Welding is a fabrication process that joins materials, usually metals or thermoplastics, primarily by using high temperature to melt the parts together and allow them to cool, causing fusion. Common alternative methods include solvent welding, using chemicals to melt materials being bonded without heat, and solid-state welding processes which bond without melting, such as pressure, cold welding, and diffusion bonding. Metal welding is distinct from lower temperature bonding techniques, such as brazing and soldering, which do not melt the base metal, parent metal, and instead require flowing a filler metal to solidify their bonds. In addition to melting the base metal in welding, a filler material is typically added to the joint to form a pool of molten material, the weld pool, that cools to form a joint that can be stronger than the base material. Welding also requires a form of shield to protect the filler metals or melted metals from being contaminated or oxidized. Many different energy sources can be used for welding, including a gas flame, chemical, an electric arc, electrical, a laser, an electron beam, friction, and ultrasound. While often an industrial process, welding may be performed in many different environments, including in open air, underwater, and in outer space. Welding is a hazardous undertaking, and precautions are required to avoid burns, electric shock, vision damage, inhalation of poisonous gases and fumes, and exposure to intense ultraviolet radiation. Until the end of the 19th century, the only welding process was forge welding, which blacksmiths had used for millennia to join iron and steel by heating and hammering. Arc welding and oxy-fuel welding were among the first processes to develop late in the century, and electric resistance welding followed soon after. Welding technology advanced quickly during the early 20th century as world wars drove the demand for reliable and inexpensive joining methods. Following the wars, several modern welding techniques were developed, including manual methods like shielded metal arc welding, now one of the most popular welding methods, as well as semi-automatic and automatic processes, such as gas metal arc welding, submerged arc welding, flux cord arc welding, and electro slag welding. Developments continued with the invention of laser beam welding, electron beam welding, magnetic pulse welding, and friction stir welding in the latter half of the century. Today, as the science continues to advance, robot welding is commonplace in industrial settings, and researchers continue to develop new welding methods and gain greater understanding of weld quality. The term weld is derived from the Middle English verb well or welling, meaning to heat to the maximum temperature possible, to bring to a boil. The modern word was probably derived from the past tense participle weld, with the addition of the letter D for this purpose being common in the Germanic languages of the Angles and Saxons. It was first recorded in English in 1590. A 14th century translation of the Christian Bible into English by John Wycliffe translates Isaiah chapter 2 verse 4 as, "They shall beat together their swords and plowshares." In the 1590 version, this was changed to, "They shall weld together their swords into plowshares," suggesting this particular use of the word probably became popular in English some time between these periods. The Old English word for welding iron was samad, to bring together, or samadwelling, to bring together hot. The word is related to the old Swedish word valla, meaning to boil, which could refer to joining metals, as in valla järn, literally to boil iron. Sweden was a large exporter of iron during the Middle Ages, so the word may have entered English from the Swedish iron trade, or may have been imported with the thousands of Viking settlements that arrived in England before and during the Viking Age, as more than half of the most common English words in everyday use are Scandinavian in origin. The history of joining metals goes back several millennia. Fusion welding processes that join metals by melting them were not widely used in pre-industrial welding. Early welding techniques used pressure to join to the metals, often with heat not sufficient to fully melt the base metals. One notable exception was a technique to join sections of large statues. In Greek and Roman lost wax casting, the statues were cast as smaller pieces, and molten bronze was poured into the joints, with temperatures sufficient to create fusion welds. The earliest known welding dates to the Bronze Age. Gold is soft enough to be pressure welded with little to no heat, and archaeologists have found small boxes made by pressure welding overlapping sheets of gold. In the Iron Age, Mediterranean societies developed forge welding. In forge welding, metal is heated to the point that it becomes soft enough for a blacksmith to hammer separate pieces together. Very early notable examples are the iron objects found with Tutankhamun, including an iron headrest and dagger. The dagger was forged from meteoric iron at temperatures below 950 degrees Celsius. Typically, wrought iron is forged at around 1,350 degrees Celsius. The ancient Greek historian Herodotus credits Glaucus of Chios with discovering iron welding. Glaucus is known for an iron pedestal welded to hold a silver crater at Delphi. The Middle Ages brought advances in forge welding, in which blacksmiths pounded heated metal repeatedly until bonding occurred. In Europe and Africa, forging shifted from open charcoal fires to bloomeries. China developed a blast furnace late in the first millennia. Forge welding was used in the construction of the Iron Pillar of Delhi, erected in Delhi, India about 310 AD, and weighing 5.4 metric tons. In 1540, Vannocchio Bringuccio published De la Pyrotechnica, which includes descriptions of the forging operation. Renaissance craftsmen were skilled in the process, and the industry continued to grow during the following centuries. In 1800, Sir Humphrey Davy discovered the short pulse electric arc and presented his results in 1801. In 1802, Russian scientist Vasily Petrov created the continuous electric arc and subsequently published News of Galvanic Voltaic Experiments in 1803, in which he described experiments carried out in 1802. Of great importance in this work was the description of a stable arc discharge and the indication of its possible use for many applications, one being melting metals. In 1808, Davy, who was unaware of Petrov's work, rediscovered the continuous electric arc. In 1881–82, inventors Nikolai Benardos, Russian, and Stanisław Olszewski, Polish, created the first electric arc welding method known as carbon arc welding, using carbon electrodes. The advances in arc welding continued with the invention of metal electrodes in the late 1800s by a Russian, Nikolai Slavyanov, 1888, and an American, C. L. Coffin, 1890. Around 1900, A. P. Strominger released a coated metal electrode in Britain, which gave a more stable arc. In 1905, Russian scientist Vladimir Mickiewicz proposed using a three-phase electric arc for welding. Alternating current welding was invented by C. J. Holslag in 1919, but did not become popular for another decade. Resistance welding was also developed during the final decades of the 19th century, with the first patents going to Elihu Thomson in 1885, who produced further advances over the next 15 years. Thermite welding was invented in 1893, and around that time another process, oxy-fuel welding, became well established. Acetylene was discovered in 1836 by Edmund Davy, but its use was not practical in welding until about 1900, when a suitable torch was developed. At first, oxy-fuel welding was one of the more popular welding methods due to its portability and relatively low cost. As the 20th century progressed, however, it fell out of favor for industrial applications. It was largely replaced with arc welding, as advances in metal coverings known as flux were made. Flux covering the electrode primarily shields the base material from impurities, but also stabilizes the arc and can add alloying components to the weld metal. World War I caused a major surge in the use of welding, with the various military powers attempting to determine which of the several new welding processes would be best. The British primarily used arc welding, even constructing a ship, the Fuliger, with an entirely welded hull. Arc welding was first applied to aircraft during the war as well, as some German airplane fuselages were constructed using the process. During the middle of the century, many new welding methods were invented, including the introduction of automatic welding in 1920, in which electrode wire was fed continuously. Shielding gas received much attention, as scientists attempted to protect welds from the effects of oxygen and nitrogen in the atmosphere. Porosity and brittleness were the primary problems, and the solutions that developed included the use of hydrogen, argon, and helium as welding atmospheres. Testing methods were introduced for weld integrity. First, vibration testing was done using a hammer and stethoscope. Later, X-ray tests were developed to see into the weld. During the 1930s, further advances allowed for the welding of reactive metals like aluminum and magnesium. This, in conjunction with developments in automatic welding, alternating current, and fluxes, fed a major expansion of arc welding during the 1930s. Russian inventor Konstantin Krenov implemented the first underwater electric arc welding. In 1930, Kyle Taylor was responsible for the release of stud welding, which soon became popular in shipbuilding and construction. Submerged arc welding was invented the same year. During World War II, submerged arc welding was widely used for shipbuilding because it allowed certain types of welds to be done 20 times faster than earlier techniques. Improvements to welding processes opened up new possibilities for construction. Previously, large metal structures had been made from metals joined mechanically with rivets, along with bolts, screws, and belts. These connected but unfused metal structures had inherent weaknesses. The steamboat Sultana killed over 1,000 passengers when its riveted boiler failed under pressure. The unsinkable Titanic sank due in part to failures in its riveted hull. In 1930, the first all-welded merchant vessel, MS Carolinian, was launched. The strength of welded steel also allowed for the creation of entirely new types of ships, notably the liquefied natural gas LNG tanker. The ASME Boiler and Pressure Vessel Code, created in response to deadly boiler failures, was used to develop the spherical tanks that contain LNG during transport. Also noteworthy is the first welded road bridge in the world, the Marcice Bridge in Poland, 1928. Early skyscrapers and steel truss bridges were built from riveted steel beams. Welding allowed for stronger and lighter structures and greater range of shapes. The Sydney Opera House's icon shape is built on a stud-welded steel frame. Gas tungsten arc welding, after decades of development, was finally perfected in 1941, and gas metal arc welding followed in 1948, allowing for fast welding of non-ferrous metals, but requiring expensive shielding gases. Shielded metal arc welding was developed during the 1950s, using a flux-coated consumable electrode, and it quickly became the most popular metal arc welding process. In 1957, the flux-cored arc welding process debuted, in which the self-shielded wire electrode could be used with automatic equipment, resulting in greatly increased welding speeds, and that same year, plasma arc welding was invented by Robert Gage. Electroslag welding was introduced in 1958, and it was followed by its cousin, electrogas welding, in 1961. In 1953, the Soviet scientist N.F. Kazakov proposed the diffusion bonding method. Other recent developments in welding include the 1958 breakthrough of electron beam welding, making deep and narrow welding possible through the concentrated heat source. Following the invention of the laser in 1960, laser beam welding debuted several decades later, and has proved to be especially useful in high-speed automated welding. Magnetic pulse welding, MPW, has been industrially used since 1967. Friction stir welding was invented in 1991 by Wayne Thomas at the Welding Institute, TWI UK, and found high-quality applications all over the world. All of these 4 new processes continue to be quite expensive due to the high cost of the necessary equipment, and this has limited their applications. Welding joins 2 pieces of metal using heat, pressure, or both. The most common modern welding methods use heat sufficient to melt the base metals to be joined and the filler metal. This includes gas welding and all forms of arc welding. The area where the base and filler metals melt is called the weld pool or puddle. The weld pool must be protected from oxygen in the air that will oxidize with the molten metal and from other gases that could contaminate the weld. Most welding methods involve pushing the puddle along a joint to create a weld bead. Overlapping pieces of metal can be joined by forming the weld pool within a hole made in the topmost piece of base metal to form a plug weld. Solid-state welding processes join 2 pieces of metal using pressure. Electric resistance welding is a common industrial process that combines heat and pressure to join overlapping base metals without any filler material. Gas welding, also known as oxyacetylene welding, uses an open flame to generate heat and shield the weld. Compared to arc welding, the flame is less concentrated and lower in temperature, about 3,100 degrees Celsius near the torch tip. This causes slower weld cooling, which can lead to greater residual stresses and weld distortion, though it eases the welding of high alloy steels. The diffuse outer envelope of the flame consumes oxygen before it can reach the molten weld pool. When working with easily oxidized metals, such as stainless steel, flux can be brushed onto the base metals. The equipment is relatively inexpensive and simple, consisting of a torch, hoses, pressure regulators, a tank of oxygen, and a tank of fuel, usually acetylene. It is one of the oldest and most versatile welding processes, but it has become less popular in industrial applications. It is still widely used for welding pipes and tubes, as well as repair work. Similar process, generally called oxy-fuel cutting, is used to cut metals. Oxy-fuel equipment can also be used to heat metal before bending or straightening. All arc welding processes use a welding power supply to create and maintain an electric arc between an electrode and the base material to melt metals at the welding point. It can use alternating current, AC, or direct current, DC. For DC welding, the electrode can be connected to the machine's positive terminal, DCEP, or negative terminal, DCEN, changing the current's direction. The process and type of electrode used will typically determine the current. Shielding gas prevents oxygen in the atmosphere from entering the molten weld pool. In some processes, the shielding gas is delivered from gas cylinders containing inert or semi-inert gas. In others, a flux coating on a consumable electrode disintegrates to create the gas. Filler material is typically added to the molten weld pool and is necessary for processes that use a consumable electrode. One of the most common types of arc welding is shield metal arc welding, SMAW. It is also known as manual metal arc welding, MMAW, or stick welding. Electric current is used to strike an arc between the base material and consumable electrode rod, which is made of filler material, typical steel, and is covered with a flux that protects the weld area from oxidation and contamination by producing carbon dioxide gas during the welding process. The electrode core itself acts as filler material, making a separate filler unnecessary. The process is versatile and can be performed with relatively inexpensive equipment, making it well suited to shop jobs and field work. An operator can become reasonably proficient with a modest amount of training and can achieve mastery with experience. Weld times are rather slow, since the consumable electrodes must be frequently replaced, and because slag, the residue from the flux, must be chipped away after welding. Furthermore, the process is generally limited to welding ferrous materials, though special electrodes have made possible the welding of cast iron, stainless steel, aluminum, and other metals. Gas metal arc welding, GMAW, is also known as metal inert gas or MIG welding, is a semi-automatic or automatic process that uses a continuous wire feed as an electrode and an inert or semi-inert gas mixture to protect the weld from contamination. Since the electrode is continuous, welding speeds are greater for GMAW than for SMAW. A related process, flux cord arc welding, FCAW, uses similar equipment but uses wire consisting of a tubular steel electrode surrounding a powder fill material. This cored wire is more expensive than the standard solid wire and can generate fumes and/or slag, but it permits even higher welding speed and greater metal penetration. As the electrode is consumed, the flux disintegrates to create shielding gas and a protective layer of slag similar to stick welding. Some flux cord machines have a nozzle that uses a shielding gas to supplement the protection from the flux. This is called dual shield welding and uses a specialized gas-shielded flux core wire. Gas tungsten arc welding, GTAW, or tungsten inert gas, TIG welding, is a manual welding process that uses a non-consumable tungsten electrode, an inert or semi-inert gas mixture, and a separate filler material. Especially useful for welding thin materials, this method is characterized by a stable arc and high-quality welds, but it requires significant operator skill and can only be accomplished at relatively low speeds. GTAW can be used on nearly all weldable metals, though it is most often applied to stainless steel and light metals. It is often used when quality welds are extremely important, such as in bicycle, aircraft, and naval applications. A related process, plasma arc welding, also uses a tungsten electrode, but uses plasma gas to make the arc. The arc is more concentrated than the GTAW arc, making transverse control more critical and thus generally restricting the technique to a mechanized process. Because of its stable current, the method can be used on a wider range of material thicknesses than can the GTAW process, and it is much faster. It can be applied to all of the same materials as GTAW except magnesium, and automated welding of stainless steel is one important application of the process. A variation of the process is plasma cutting, an efficient steel cutting process. Submerged arc welding, SAW, is a high-productivity welding method in which the arc is struck beneath a covering layer of flux. This increases arc quality since contaminants in the atmosphere are blocked by the flux. The slag that forms on the weld generally comes off by itself, and combined with the use of a continuous wire feed, the weld deposition rate is high. Working conditions are much improved over other arc welding processes, since the flux hides the arc and almost no smoke is produced. The process is commonly used in industry, especially for large products and in the manufacture of welded pressure vessels. Other arc welding processes include atomic hydrogen welding, electroslag welding, ESW, electrogas welding, and stud arc welding. ESW is a highly productive single-pass welding process for thicker materials between 1 inch and 12 inches in a vertical or close to vertical position. To supply the electrical power necessary for arc welding processes, a variety of different power supplies can be used. The most common welding power supplies are constant current power supplies and constant voltage power supplies. In arc welding, the length of the arc is directly related to the voltage, and the amount of heat input is related to the current. Constant current power supplies are most often used for manual welding processes, such as gas tungsten arc welding and shielded metal arc welding, because they maintain a relatively constant current even as the voltage varies. This is important because in manual welding, it can be difficult to hold the electrode perfectly steady and as a result, the arc length and thus voltage tend to fluctuate. Constant voltage power supplies hold the voltage constant and vary the current, and as a result are most often used for automated welding processes, such as gas metal arc welding, flux cord arc welding, and submerged arc welding. In these processes, arc length is kept constant, since any fluctuation in the distance between the wire and the base material is quickly rectified by a large change in current. For example, if the wire and the base material get too close, the current will rapidly increase, which in turn causes the heat to increase and the tip of the wire to melt. The type of current used plays an important role in arc welding. Consumable electrode processes such as shielded metal arc welding and gas metal arc welding generally use direct current, but the electrode can be charged either positively or negatively. In welding, the positively charged anode will have a greater heat concentration, and as a result, changing the polarity of the electrode affects weld properties. If the electrode is positively charged, the base metal will be hotter, increasing weld penetration and welding speed. Alternatively, a negatively charged electrode results in more shallow welds. Non-consumable electrode processes, such as gas tungsten arc welding, can use either type of direct current, as well as alternating current. However, with direct current, because the electrode only creates the arc and does not provide filler material, a positively charged electrode causes shallow welds, while a negatively charged electrode makes deeper welds. Alternating current rapidly moves between these two, resulting in medium penetration welds. One disadvantage of AC, the fact that the arc must be reignited after every 0 crossings, has been addressed with the invention of special power units that produce a square wave pattern instead of the normal sine wave, making rapid 0 crossings possible and minimizing the effects of the problem. Resistance welding generates heat from electrical resistance in the base metals. 2 electrodes are simultaneously used to press the metal sheets together and to pass current through the sheets. The electrodes are made from highly conductive material, usually copper. The higher resistance in the base metals causes small pools of molten metal to form at the weld area as high current is passed through. Resistance spot welding is a popular method used to join overlapping metal sheets of up to 3 millimeters thick. The advantages of the method include efficient energy use, limited workpiece deformation, high production rates, easy automation, and no required filler materials. Weld strength is significantly lower than with other welding methods, making the process suitable for only certain applications. It is used extensively in the automotive industry. Ordinary cars can have several thousand spot welds made by industrial robots. In general, resistance welding methods are efficient and cause little pollution, but their applications are somewhat limited, and the equipment costs can be high. A specialized process called shot welding can be used to spot weld stainless steel. Seam welding also relies on 2 electrodes to apply pressure and current to join metal sheets. However, instead of pointed electrodes, wheel-shaped electrodes roll along and often feed the workpiece, making it possible to make long, continuous welds. In the past, this process was used in the manufacture of beverage cans, but now its uses are more limited. Other resistance welding methods include butt welding, flash welding, projection welding, and upset welding. Energy beam welding methods, namely laser beam welding and electron beam welding, are relatively new processes that have become quite popular in high production applications. The two processes are quite similar, differing most notably in their source of power. Laser beam welding employs a highly focused laser beam, while electron beam welding is done in a vacuum and uses an electron beam. Both have a very high energy density, making deep weld penetration possible and minimizing the size of the weld area. Both processes are extremely fast and are easily automated, making them highly productive. The primary disadvantages are their very high equipment costs, though these are decreasing, and a susceptibility to thermal cracking. Developments in this area include laser hybrid welding, which uses principles from both laser beam welding and arc welding for even better weld properties, laser cladding, and X-ray welding. Like forge welding, the earliest welding process discovered, some modern welding methods do not involve the melting of the materials being joined. One of the most popular, ultrasonic welding, is used to connect thin sheets or wires made of metal or thermoplastic by vibrating them at high frequency and under high pressure. The equipment and methods involved are similar to that of resistance welding, but instead of electric current, vibration provides energy input. When welding metals, the vibrations are introduced horizontally, and the materials are not melted. With plastics, which should have similar melting temperatures, vertically. Ultrasonic welding is commonly used for making electrical connections out of aluminum or copper, and it is also a very common polymer welding process. Another common process, explosion welding, involves the joining of materials by pushing them together under extremely high pressure. The energy from the impact plasticizes the materials, forming a weld, even though only a limited amount of heat is generated. The process is commonly used for welding dissimilar materials, including bonding aluminum to carbon steel in ship hulls, and stainless steel or titanium to carbon steel in petrochemical pressure vessels. Other solid-state welding processes include friction welding, including friction stir welding and friction stir pot welding, magnetic pulse welding, co-extrusion welding, cold welding, diffusion bonding, exothermic welding, high-frequency welding, hot pressure welding, induction welding, and roll bonding.